Now that we've looked at Hooke's law for the forces of springs, so let's look at the potential energy in springs. So our kinetic energies are 1/2 mv squared. Our potential energies because of springs are 1/2 k delta S squared. In this problem, we have a spring-loaded toy gun launching a plastic ball. So we have a before where the spring, so this is our spring, is compressed. We have our ball. And then after, we have our spring fully uncompressed and our ball leaving, being fired. So we're told that the mass of the ball is 10 grams. Let's convert that now to kilograms. So we're going to divide it by 1,000, 0.01 kilograms. We're told the spring constant, K, is equal to 10 newtons per meter. And then it's compressed, delta S, 10 centimeters. And let's convert that to meters now. So 10 centimeters is 0.1 meters. When the trigger is pulled, the spring releases and shoots the ball out. What is the speed? Here. So here at the beginning, the velocity is 0. So before, our total energy is equal to kinetic plus potential from the spring. We'll call that initial. So our initial energy is our kinetic energy initial, which is 0 because the velocity is 0, but plus the spring potential energy, which is 1/2 K times 10 delta S 0.1 squared. So our initial energy is 1/2 times 10 times 0.1 squared. So 0.1, 0.01. So this is 1/2 times 0.1, 0.05. And this is energy. It's in joules. Remember, a joule is a kilogram meters squared per second squared. So our final energy is equal to our kinetic energy final plus our spring energy final. Since the spring is no longer being touched, we get US here is 0. So our energy final is just 1/2 mv squared plus 0, 1/2 mv squared. So using the law of conservation of energy, EI equals EF. 0.05 is equal to 1/2 mv squared. 0.05 is equal to 1/2 our mass of our ball is 0.01 v squared. So this is 2 times 0.05, 0.01. So 2 times 0.05 divided by 0.01 gives you 10. V is equal to the square root of 10. Which is 3.16 meters per second.